Hi, so this is our penultimate session workshop on CellOracle, and today Kenji's going to be guiding us through how to interpret the CellOracle output. Okay, Kenji.
Okay, so today I'm going to talk about the network, how to do the network analysis, and I will explain how to analyze your network using some kind of network score or graph theory. So in the last session we got we finished calculation of your GLN. So hopefully your network was saved. Sorry, your network was in this object, links object. So now I'm going to show how to look at your data. So first, your network was in this object, and hopefully you remember we finished filtering. So we have the filtered filtered network here. So this is the dictionary object, Python dictionary. So you can get one object like this. If you want, you can save this this data table, and you can analyze by yourself. I mean, in the CellOracle, we provide some method or function to analyze these network. But if you want to use if you want to analyze the network using totally different program, you can do that. For example, if you save this this network table, you can use my recommendation is Sidescape. This is a network program for the network analysis, and you can import our network to the Sidescape, and you can analyze using the many graphical and cool stuff. But here, the CellOracle have several cool function to analyze the network. So I will explain how to use that. Okay, so in your object, you have so this is the single cell RNA-seq data of your this is your single cell RNA-seq data. For example, you have, for example, here you have many cluster like erisor 0, 1, 2. There are 25 clusters here. So you have calculated the gene regulatory network for each cluster. I mean, you have many GRN, which represent the cluster specific connection, or the cluster specific gene regulatory network. So in the CellOracle, we can visualize the gene regulatory network in if you want to focus on this cluster, you can set like this, and you can visualize the network score like this. So in the CellOracle, we calculated many network score because it's really useful to use the network scores. For
Kenji,
example,
I have a question. So it's more of
yes.
a general question here. With CellNet, we used GRN inference to assess the similarity of cell types to each other. So to assess the similarity of engineered cell type to the target population, so the in vivo, the bona fide cell type. Here, is there any kind of metric to assess the similarity of these inferred GRN configurations to each other? So if you want to take, two of your clusters that you think are quite similar, is there a way we could devise some metric to look at the similarities and differences between these networks beyond what you'll show today?
So in general, there is some method to measure the similarity between the network, but in the CellOracle we do not have any function for to calculate the similarity. But we we have some function, but to analyze the GRN, but this function is for to analyze the gene function or the gene module or something. We cannot we don't have any method to know the similarity here. So hopefully we can do. In theory, we can export the network and we can calculate the similarity using the two different algorithm, or but anyway.
Yeah, it could be something that's worth exploring in the future if people think that's something that would be helpful.
Yeah, we can do that. Yeah. So here these are the list of your network score. Using some R library, we calculated many network score like this here. You can see the score is stored in this object, in this attribute margin.score. Okay, so here I do not explain the single detail of this network score, but in brief, these are for example, like this degree, the score of the degree, or degree centrality. This one is kind of one of the most important score. So let me explain this one first. For example, the degree means the number of edge in the network. The node is single gene, and each single gene have the degree centrality score. This is normalized degree centrality score. So the maximum is 1 and the minimum is 0. Okay, for example, this one, STAT3, this is a really important transcription factor. So this factor have many connections. So the degree centrality of this gene is really high. And for example, we can visualize the the network score, focusing on this cluster like this.
So Kenji, if you go back up to that table,
yep,
you were just pointing out. So we've got the degree centrality for STAT3, but then so couple down E2F4. So that score is. Does that mean it's connecting to twice as many genes as STAT3?
Yes, it is.
Okay.
Yep. So the degree centrality score means the number of edge. So this, if the for example, E2F4 have the 0.3 and STAT3 is 0.15. So maybe the E2F4 have the twice edges compared to STAT3. So in many cases, for example here, if the gene have really high degree centrality score, it's tend to be really important gene. I mean, for example, E2F4 is a really important gene for the that regulates many stuff in the hematopoietic stem cell differentiation. So, which is really important. I mean, if you look at this table, maybe you can pick up some key regulatory genes. So, yeah.
In terms of this table, Kenji, so we've had some users, some pioneers of CellOracle that have reported finding some non-transcriptional regulators in this table. And so maybe we can explain to people why they might see that. It doesn't happen very frequently.
Okay, yeah. So, for example, here, degree centrality, here we have like 3 types of degree centrality: all, degree centrality in and out. So, for example, the degree centrality in means we counted number of edge which coming in from different gene. I mean, for example, if one gene have the high degree centrality in, which means this gene is regulated by many genes, and the degree centrality out is the opposite score. I mean, degree centrality out is counting the edge which come out. I mean, the transcription factor have the really high degree centrality out score. Degree centrality or mean the sum of these 2 score. So if, for example, if one gene is regulated by really many genes, and for example, this gene is not transcription factor, but if the gene is regulated by many genes and which have many regulatory connection, which can be exist in this list. I mean, this list can include the non-transcription factor, but I think in many cases you will see the really many transcription factor in this list. I guess, yeah. I think the ETF4, LETA2, and FE2, yeah, these are all transcription factor, I think.
Yeah, it's definitely been our experience that we see transcription factors and transcriptional regulators primarily in these lists.
Yeah, and here is the list of the degree centrality in. I mean, this gene is not. I think this is not transcription factor. So this is gene are connected by many transcription factor and regulated by many transcription factor. Okay. So yeah. And I mean, if you are interested, if you want to know the detail of this score, please like Google like degree centrality or something. I think there is kind of really good good explanation on the web, so you can find the really cool visualization. I think. I mean, yeah. So here we provide basic score here. So you can see like closeness centrality or eigenvector centrality or page rank or something. We provide many score, but you don't need to look at all of them. Just please look, just use the if you need the score. Okay. So hopefully you can pick up important gene using this score or rank. Maybe in many cases your aim of your analysis is like to pick up important gene or to pick up key regulatory gene maybe. But here one problem is like this gene include this gene not only this gene is for example GATA2 is really important gene for the MEP, I mean MEP cluster, but the E2F4, for example, is kind of the really universally important gene and generally important, and ubiquitously expressed in the hematopoietic cell. So maybe one good function is here. You can compare two GRN using this function. For example, here, if you want to compare degree centrality in MAP or GMP, you can do that like this. So here, we are just visualizing the two centrality score in the scatter plot. For example, here, you will see like E2F4 is really high in the both cluster, GMP cluster and MEP cluster. Okay, but before talking about these cluster, please let me briefly explain what is a GMP and MEP. So here is the like illustration of the developmental trajectory or developmental pathway. So the MEP and GMP, both MEP and GMP are originated from common progenitor cell. Common myeloid progenitor cell cluster here. I mean, these are kind of like similar cluster, but differentiate into totally different lineage. So here we want to compare MEP and GMP here because, for example, we want to know what factor is important for the determination of the lineage commitment. So we can compare GMP and MEP here. And for example, here, E2F4 is really, the score of E2F4 is really high in the both cluster. Maybe it means that this factor is really important for the both. And I think which is true, which may be true because the E2F4 is involved in very general function, for example, cell cycle or many really like many basic biological event. But for example, here we can see GATA2 is really high in the MEP cluster, and GATA2 is known to be important in the MEP lineage. So it's agree with this. This data makes sense. And KLF1, which is important for the MEP0, and it's known that KLF1 is really important for the erythrocyte differentiation. So, I mean, if you compare to GRN, you can know what factor is important for the different phenotype. I mean, if you look at this table, maybe you will get the many genes, and which include like housekeeping gene or like non-specific gene. But here, if you compare to score, that's what if you compare score over the mini cluster, you can know which is the important in the specific cluster. And again, for here we can see the like ILF8, which have high score in the GMP lineage, and it's known that ILF8 is really important for this lineage. So you can pick up the cluster specific key literature gene using this comparison. Okay, and not only degree centrality, you can visualize like different factor, eigenvector centrality or Betweenness centrality. So this score means for example, eigenvector centrality looks a little bit different compared to the degree centrality. It's because the eigenvector centrality is this score represents the not only direct connection, but also it's represent the indirect connection. So we can get a little bit different factor. Yeah. So the betweenness centrality is also important. Yeah. Okay. So here.
So Kenji, I think these two different.
Yeah.
Oh, go for it, Christine.
Throughout this process, I've gotten a couple questions about the scale of, and numbers on each of the axes. Can you touch briefly on what those are, and when you see that they're drastically different, what that can mean?
Yeah, I think in yeah. So here the each axis means. So I didn't do any kind of numerization between two in this scale. But but the degree centrality score is already normalized, so it means that usually you will get the like really similar scale, I think. And if you look at really different cluster, maybe you will see the really huge difference on the scale. But I think in many cases you will get really like similar scale pattern because these score again, for example, eigenvector centrality or degree centrality is already normalized. So maybe hopefully many score exist in between 0 and 1. So maybe it's fine. But in the betweenness centrality, which the which score is not like similar sometimes. In this visualization, we are showing like this is the max between centrality score, and this is the max of the x-axis. So we are showing just we are looking at the different scale, but maybe the important stuff is you can just look at the difference between these score, and I don't know what is there is no method to do the thresholding, so I can just say this score is like highly enriched in this cluster, and this score is highly enriched in this score. And hopefully you can see like how about this gene YBX1. I don't have the answer. I don't know if the scale is really different. Sometimes we do not know how to interpret these genes, but maybe the important difference exists in here or here. So
I think as well it would be helpful to give people a broad kind of idea of what these measures mean as well, in terms of how is betweenness centrality, eigenvector centrality different to degree centrality as well, just in really basic terms.
Yeah. So okay. So for example, the degree centrality, which is the number of edge and which is normalized. But here, betweenness centrality is which is not normalized score. So which have like 6,000 or 3,000. So anyway, what is the betweenness centrality? Okay. Honestly, I don't want to explain this score because it's clearly complicated, but so okay, for example, if we have one gene, sorry, if we have 3 genes here, for example, three nodes, and we have 2 edge here. And the betweenness centrality means that which for example, if we look at the connection, maybe if this gene or this node connect these two node, so if we block this node, these two connection will be obstructed. And the number of this obstruction means the betweenness centrality. I mean, the betweenness centrality represent this gene is really important because this gene connect many gene or many nodes.
So you say that gene is important for propagating a signal through a network, essentially.
Yes, exactly. Yeah. The number means that if we block this connection or this node, this number will be lost. Will lose in the network. So this, betweenness centrality represent direct and indirect connection, and which this gene is really important because this gene is propagating many signals in the network. Okay. Anyway, if you want to, if you have question about this score, please Google first. So maybe you can know what the score means, or and okay. Anyway, so one important function, one unique point in the CellOracle is you can compare two GRM focusing on one score. This comparison does not necessarily mean the similarity of the network, but you can compare the gene, the importantness of this gene focusing on this score, so which may be really useful. Okay, so one more thing I want to introduce is this function, per score per cluster. So for example, this analysis, you can visualize gene score. For example, focusing on data 2, you can visualize each score is in like this. The data 2 is known to play important role in the MAP lineage, but it's in this figure, the data 2 score, for example, degree centrality, data 2 score decrease according to this over the clusters, like the MAP 0 or MK state, so MK phase, the data 2 score is really high, but it decreases according to the differentiation. So it's known that data 2 is really important for the progenitor or stem progenitor state in the MAP lineage. So we can know the we can know the quantitative dynamics of this gene. Yeah. So if you want to something else, you can change this this value, gene of interest, and you can see that how the network change over the differentiation or the programming. Hopefully this
so Kenji, in terms of the different degrees centrality metrics here, I think it's interesting in this MEP cluster, for example, with GATA2. So degree centrality, we're looking at the the number of edges in total. But then eigenvector centrality in this context gets really interesting. So, we see that the MEPs have a reasonable amount of connectivity in terms of GATA2, but then the eigenvector centrality is high. And correct me if I'm wrong, that indicates that in the MEPs, GATA2 is likely to be, it might not have as many connections in terms of number of absolute edges, but then the other genes it's connecting to are potentially quite well connected within those networks. So it kind of gives it a little bit, gives it eigenvector centrality. That's an interesting metric, I think, just to point out to people here.
Yeah. So each score mean a little bit different features. So I mean, if you look at the score, like the degree centrality and eigenvector centrality or Betweenness centrality, and if you see like different phenotype, maybe this means that your gene, I will not say, by looking at the score pattern, you can infer the role or function of your gene. So maybe, the eigenvector centrality means this is generated by the direct and indirect connection. So hopefully this score is showing a little bit more about the degree centrality. Okay, and if we let me show one more different gene. So here, if we show the CDP alpha gene, here we can we detect some score here, but we cannot see any score here, the ellipsoid side cluster, which means that this gene do not have any connection in this cluster after filtering. So if you cannot see anything in your table, it means that your interest doesn't have any connection in the table. I mean, this is not a bug. This is just this means just your interest do not have any connection here. Actually the CBP alpha is known to play a really important role in this lineage, GMP lineage. So it makes sense. It's biologically feasible. Okay, and okay. So one more thing, the gene cartography and analysis. This is the method for the GRN, but this method, okay, let me explain what is the gene cartography analysis. So we look at the connection and we look at the network module. For example, first we will calculate the network module. For example, here we have two network module here, and we will calculate the number of edge inside the network module, and we also count the number of edge between the module. So based on these two score, we will make the scatter plot, and we classify each gene into the 1, 2, 3, 4, 5, 6, 7 into the seven groups. So based on this analysis, we can know you can classify your gene into the 7 functional group, or you can know this gene is the importantness of this gene. In brief, go back here. For example, here, if we visualize the gene cartography in the ellipsoid side cluster, we can see like the GATA1 and what GATA2 exists here. this is a relatively important cluster. I mean, if you find your gene exists here, the top right group, it means that this gene is really, really important. But if you found this gene, if you found one gene exists the left bottom group here, it means your gene have really small connection and which is not important. Maybe. So based on this analysis, you can um, classify your gene into several groups. For example, GATA2 was we can see like GATA2 is really important in the many side cluster here, or like in GMP, the early GMP cluster. And that's important in the late side differentiation lineage. I mean, using this score or using this analysis, you can classify your gene into the several groups, and you can assume like this gene may be important in this phase, but not important in this cluster. So anyway, if you want to know the detail of this method, you can read this paper. The so here is many detailed explanation. Anyway, you can do the gene cartography analysis easily, and you can visualize your gene of interest like this. So hopefully it helps you to find the key regulatory gene in one cluster. Okay. We can show one more stuff. Maybe this is the last thing. So, so for example, yeah, you know, we have the score for the degree centrality. So not only just get the plot, but also we can visualize in the box plot or bio plot or something. Yeah, this is just visualization. Not the matters of visualization. Okay, and the one more stuff. We can calculate the network entropy based on your GRN structure. The network entropy is based on the the network, the number of edge, and the strength of your network connection. So in brief, your network GRN have small network entropy score in the differentiated cluster, and you will see the high network entropy structure in the stems or progenitor less differentiated cluster, I guess. So anyway, if you want to know the detail of network entropy, you can Google the network entropy or biological.
Yeah, I think we have some typos to kind of clean up in this, but I can help go through that as well, Kenji, if you need any proofreading.
Sorry, yeah. Yeah, sorry. I mean, maybe there are so many typos, so please let me know. I will
you've put together a lot of documentation for this as well, so it's going to happen. So, but,
yeah. Anyway, so yeah. So I want to say we can do many network analysis based on your GRN. So the CellOracle provides some network score, and you can use this score. But if you don't like this method, you just do the analysis by yourself. It's completely fine. We just provide the basic function for the analysis. And one of the unique point of CellOracle is we can calculate GRN for each cluster. So maybe we can compare, or we can see how it changes over the, over differentiation or something. This is the unique point. Okay. Any questions or suggestion or something?
That's great, Kenji. Thank you. So one point to make is in the preprint, the CellOracle preprint, we really carefully go through this analysis of hematopoiesis to show people how we can pick out important genes. But then we also apply CellOracle analysis to reprogramming fibroblasts to induce endodermogenesis and really walk people through how they can use CellOracle to find some of these interesting genes, and in our case, how the transgene is connected through the reprogramming process, and some, really exciting results there, I think. So I would definitely encourage people to read the preprint as well as go through this workbook, because it's gonna help you guide you through understanding and interpreting the data result, or that's our hope, at least.
Yeah, please lead with our CellOracle preprint. Maybe this gonna be really good example of how to use the CellOracle. Yeah. And on the web tutorial, we provide the notebook. Please look at the notebook. Yeah. Hopefully you can find the practical information on the notebook.
Any questions?
I think one key thing that we might
go for it.
Sorry, I was saying that one thing that we might want to emphasize is how using CellOracle is different from doing differential gene expression analysis, where with CellOracle you're going to find so many different things that might be not uncovered when you do the differential gene expression analysis.
Yeah, exactly. Please, thank you for saying that. I mean, even if there is no difference in terms of the gene expression, but maybe you can find some kind of difference in the gene regulatory network structure. So this is gonna be really cool analysis. Yeah. The CellOracle will find out the difference based on the gene to gene connection. So hopefully you can get more deep or mechanistic insight into your single cell RNA-seq data.
Any other discussion points? Because it's always, I stop recording and then you start having the interesting discussion. So anything to raise before I stop recording?
One thing, Kenji, that I've thought about or kind of been curious about is how does the number of genes that you start with in your data set, how does that affect the analysis you're able to do?
Yes, the usually in the pre-processing step, we filtered out many. We pick up just like 3,000 gene or 2,000 gene. I mean, if you have like many gene, your GRN will have the like noise, or I recommend to pick up like only a few thousand gene, like instead of or genes. But I don't know what is the best number, but in like I feel like it's better to use only a few thousand gene. Yeah, I usually use 2000 or 3000. Just.
And you just chose like the most highly variable genes when you do that, right? Similar
Yes.
to a Seurat analysis or something. So one thing I've also been curious is that maybe what if there are, more transcriptional regulators that don't get included in that highly variable list, right? So I wonder if it might be helpful to have maybe even do this analysis kind of multiple different ways where you just choose the highly variable genes or choose a list of transcription factors or kind of combine the two, right, to see if maybe you see if there's any more, any information maybe in some of those genes that aren't included, especially thinking of transcription factors and how just because their expression is so low, how does that affect how often they're included in the variable genes or not, right? Because those are genes that we could be, might be really interested in.
Yeah. I think it's a really good suggestion. I mean, I haven't tried like to pick up. I mean, so far I just pick up highly variable gene or highly expressed gene, but maybe we can do better filtering method, I guess. So yeah, maybe like you say, we can pick up just transcription factor first, and then we can do the gene filtering. Like we can do like two-step filtering or something. Maybe it's gonna be really interesting. So I haven't tried, but I will try it.
I
have kind of a.
Go on, Emily.
I had a kind of a similar question or idea. The question about the scales of the betweenness centrality versus the other metrics, like the betweenness centrality scale was quite large, but you hadn't scaled that number. I was wondering if it was potentially a difference in network sizes between those clusters, and also if there was a way to scale that metric. Obviously, you understand the math behind that a little bit better than we do right now, but I don't know, what are your thoughts?
Yeah, I think it's a really good point. I think, yeah. So yeah, so far I mean, I have not do like scaling. I mean, scaling for the betweenness centrality, but yeah, as you said, network scale. I mean, network size can affect the betweenness centrality. Yeah, it's really true. So in the CellOracle analysis, in the first step, we did the edge filtering in the first step. So maybe in this step, we applied the exact same filtering function for all GRN. So this is why I didn't do any additional scaling or something. But yeah, maybe we can. The network size is kind of really important point. So I mean, now we just pick up top 2000 gene or top 3000 edge in the first process, but maybe we can do something different for the filtering or like network network size selection or something. Yeah.
I wonder if there would be a plot or some way to visualize network size as well, because even if you don't scale the betweenness centrality, if there was just a sanity check plot somewhere to say, oh, maybe the difference here is just that the sizes are still different despite kind of consistent filtering.
Yeah.
I had a question, Kenji. So the data which you have been using for all of these analysis, is that available as a pre-processed CellOracle object or something which you can directly load and use? Or if we have to do the same analysis with your data set, will we have to start with like the count matrix or something?
Yeah, I mean, the single cell data here I'm using here is available. I mean, you can load using the scanpy function, and hopefully you can reproduce really similar or maybe exact same result. I think in the CellOracle we do not provide the result of the GRN analysis, but you can just, I mean, if you use the tutorial notebook, you can reproduce really similar or same result, I guess. Yeah.
Okay, thanks.
Yeah.
Yeah, that pool data set's really nice to, I think, explore some of this, especially because hematopoiesis has been so well defined.
Yeah. One thing I know Sam kind of mentioned early on was about is there any quantitative kind of measure to determine how similar, you know, these networks are from cluster to cluster. And I thought that definitely sounded interesting and could certainly be useful, especially if, kind of like I mentioned before, like it would be interesting to try to use these GRNs to guide the clustering almost, or confirm clustering results, you know, or should these two clusters be merged together or separated kind of thing, right? And being able to easily, you know, assess how similar the networks are would be really helpful in that.
Yeah, it's a great idea. I like that. It's kind of coming back around to that conversation on batch effects again. So, you know, if you've got two samples from the same tissue, bad batch effects, if you infer the gene regulatory networks, how different do they look between that? Any more questions, comments? Okay, thanks very much, Kenji. That was fantastic. So next week, we'll be getting into, once you've identified the transcription factors that you're interested in from these analyses, or if you have a pet transcription factor that you're particularly interested in, then we'll guide you how to simulate perturbation of that factor and the impact that has on your cell expression profile. Okay, thanks.
Thank you.